Now, let us discuss about one of the most important law in the electromagnetic theory. This is the Coulomb's law. The Coulomb's law. So far, we described the electrical property of the charge qualitatively. Okay, we say that we have two types of charge. We know that the same charge repel, the different charge attract. Now, if we want to describe this property quantitatively, how can we do that? The first one that expresses this knowledge quantitatively is Coulomb, was Coulomb. Okay, Charles Coulomb, which is a French scientist, and by doing the careful experiment, he showed that if you have the charge with the amount of the charge is equal to Q1, you put this charge next to the charge Q2. And first, let's assume that these two charges is a point charge. It means that the size of the object of these two objects is small compared to the distance between these two objects. Okay, this is maybe oversized, but the meaning of the point charge is that, okay, change this. This is too big. Okay, so if this is the charge Q1 and this is the charge Q2, and the size of these two objects, the charge object, these two charge objects, are very small compared to the distance between these two objects. We can say that they are point charge. Okay. Now, we know that there is the electrical interaction between these two charges. But what is the amount of interaction? Coulomb said that we can write down the equation of the force between these two charges. Okay, we may write it as a Fe to say that it is an electrical force. Okay, change it with small e, and it's equal. The magnitude is equal to this equation, K Q1 Q2 over R squared. This is just the magnitude of Q1, the magnitude of Q2. Okay, this is the magnitude of the force between these two charges. And R is the distance between these two charged objects. Okay, we call this the Coulomb's law. We express the force between these two charged objects qualitatively. Okay. K is the Coulomb constant. K is a Coulomb constant. Okay, it's a constant that we may fit to the experiment. Okay, and if we use the SI unit, we will have that Q, the unit of Q, both Q1 and Q2 is Coulomb. if you write it in the full name, you will do the small letter. The first letter has to be small, but if you use it in short, it's a capital letter. So in SI unit, the charge has a unit of Coulomb. Okay, and in SI unit, we will have that the Coulomb constant K is equal to it's about 8.9876 8.9876 times 10 to the 9 with the unit of Coulomb meter square per Coulomb Newton meter square per Coulomb square. Okay, so this is the value of the Coulomb constant. We can also write down the Coulomb constant as the 1 over 4 pi epsilon 0. Okay, where epsilon 0 is a permittibility, permittibility permittivity of the free space. This epsilon 0 or epsilon naught is the permittivity of free space. We will discuss the meaning of epsilon 0 later. Anyway, we have that the value of the epsilon 0 is 9.9542. 9.9542 times 10 to the minus 12. Okay, 10 to the minus 12 with the unit of Coulomb square per Newton meter square. Coulomb square per Newton meter square. Okay, that is the value of the permittivity free space. And in SI unit, we also have the value of the fundamental charge, which is the magnitude of the electron charge. That we have the electric charge is equal to 1.60218 times 10 to the minus 90 10 to the minus 90 Coulomb. Okay, that is the fundamental charge. Now we know that we can see that this is the magnitude. Okay, it's the magnitude of the force between the charge Q1 and Q2, but force is a vector. Okay, so it means that to complete this equation, we have to write down this equation in the vector form. Okay, we can write this as a F12 is equal to the K Q1 Q2 over R12 square times the unit vector R12. Okay, so let's see the meaning of this equation. this F12 is the force on the charge 1 due to the charge number 2. So this is the F12. Okay. Sorry. Be careful on this because we can write down this notation many ways. Here I follow the survey notation. So here we have that F12 is the force from the charge number 1 on the charge number 2. Okay. And the unit vector R12 is the unit vector that point from charge number 1 to charge number 2. R12 is equal to the distance from the charge number 1 to charge number 2. So this is the vector form of the Coulomb's law. You can see that this vector form includes both the magnitude. Okay, you can see that the magnitude of this F1 is equal to this Fe. And also it includes the direction of the force F12. For example, if Q1 and Q2 have the same sign, if Q1 is positive, for example, and Q2 is positive, for example, you can see that Q1, Q2 have the same sign. It means that Q1 times Q2 is positive. Okay, so it means that they have the same sign. Okay, so it means that, for example, if this is a positive and this is positive, and this is true also if Q1 is negative and Q2 is negative, because if they are both negative, you will have the Q1 times Q2 is positive. Okay. Now you can see that the direction of F12 point away from Q1 like this. Okay, so this, if you look at this expression, Q1 times Q2 is positive. This unit vector point from Q1 to Q2. So it means that the direction of F12 point from Q1 to Q2. So this direction is correct. Now, if Q1 and Q2 have different sign, for example, if Q2 is negative, okay, so it means that if Q1 and Q1 times Q2, if Q1 and Q2 have a different sign, we have the Q1 times Q2 is negative. Okay, this is the same. If Q1 is negative, Q2 is positive. Q1 times Q2 will be negative. Now, if you look at the force F12, you can see that since Q1 times Q2 is negative, it means that F12 has the opposite direction compared to R12 because this is negative. So F12 is a negative of R12, I mean the direction. So we will have that F12 point on this direction. Okay, you can see that this is correct because these two charges have a different sign. So we have the attractive force that Q1 attracts Q2. Okay. Now, what is about the force F21? F21. The force F21 is the force on from the chart number 2 on the chart number 1. You can see that we have that this is the, we can write down this is an R21 also. So we can write that F21 is equal to the K Q1 Q2 over R21 square times R21, the unit vector R21. Okay, this is the same form, we just switch the index of 1, 2 into 2, 1. Now you can see that R12 is the distance from Q1 to Q2 and R21 is the distance from Q2 to Q1. So they are equal. R12 is equal to R21. But R12, the unit vector here, R12 is equal to the minus of R21. Their magnitude are the same, is equal to 1 because it's the unit vector, right? But the direction are opposite. So we have that R12 is the minus of R21. Substitute this and this into F21, we will have that this equal to minus of F12. Okay, it's a minus of F12. So we have that F21 is equal to the minus of F12, which is great. You can see that this is F12 and this is F21. In the opposite direction, the magnitude is their magnitude are equal, but the direction are opposite. Okay, and we can also say that these follow the Newton third law. Follow the Newton third law because this is the action-reaction pair. They have the same magnitude but point in the opposite direction. Okay, so we have the Coulomb's law here.